Hello everyone, and welcome back to our discussion of elementary probability theory. In this video, we're going to be discussing variations of the binomial and the multinomial probability functions that are commonly known as the hypergeometric and the multigeometric probability mass functions. So what was the binomial PMF? So that represented the number of successes in a finite sequence of independent binary trials. In particular, if you had the probability of success PS and the probability of failure PF, which are complements of each other, since it's a binary partition of the probability space omega, then you can find this particular probability. Now, one thing that I was emphasizing when we were discussing binomial probability mass functions is that these were percentages, not ratios. Right, so and the same thing happened for the multinomial distribution as well. So pretty much what the hypergeometric and multigeometric PMFs are going to allow us to do is consider when we do have ratios, how are we going to deal with those probability things, which can be viewed as more precise versions of binomial and multinomial PMFs. So now what we're going to do is we're going to assume a couple new things. So we're going to assume the following. The first thing is that we're going to assume that the sample size is bounded above by capital N, the population size. 2, the number of successes is also going to be bounded above by capital K, and obviously capital K is going to be bounded above by capital M, and moreover the number of failures will be bounded above by capital N minus capital K. So, using these particular objects, we can say, oh, what is the probability of success? Well, the probability of success is going to be equal to the number of successes divided by our population size n, and also the probability of failure will be equal to its complement, 1 over k divided by m. Right? So we're like, okay, PS equals k over n, PF equals 1 minus k over n. Therefore, can we just replace PS and PF in the binomial multinomial probability mass functions to get a more precise answer? The answer is no. So just replacing PS and PF by k over n and its complement does not consider how the rearrangements of those successes and failures interact with the rearrangement of the samples of size n within our population of size capital N, right? And so technically there's 3 different rearrangements: the rearrangements of the successes, the rearrangements of the failures, and the rearrangements of the samples within our population P. So let's see if we can frame a hand-wavy, I guess, definition or derivation of the hypergeometric distribution. So our event inside of omega needs to be of the structure x successes, and n minus x failures, right? And that obviously has to be out of, so x successes out of k possible successes, right? And the rearrangement of all of those. And the n minus x failures, that's obviously going to be out of capital N minus capital K possible failures, right? And keep in mind that these particular objects are going to be independent events once partitioned. So what is the probability of this particular event, E? So the probability of E is going to be equal to the number of those x success rearrangements multiplied by the size of those x or n minus x failure rearrangements. So n minus x failure rearrangements, all divided by our n sample size rearrangements, and obviously this is going to be out of our capital N possible outcomes. So once we look at this from the combinatorial perspective, this is going to be equal to what? So how many successes are possible? That's obviously k, and how many do we want? We want x, and we want any rearrangement of those. So if x is the number of successes in our sample of size n, n minus x will be the number of failures, and capital M minus capital K will be the number of failures for which those n minus x failures could be pulled from. And then we need to divide by the number of rearrangements of our particular sample from our population size of size m. So this 3 combinatorial statement is actually known as the hypergeometric. So the hypergeometric probability mass function. right? And obviously there's a more formal way to sort of build that, but one of the examples we did several videos ago actually derived this through an example that's actually what it came out to. So once you have a hypergeometric random variable identified, what would be its expected value and what would be its variance? So recall for binomial, the expected value of x will be equal to n times p, and the variance of x is going to be n times p times 1 minus p. So these were the binomial versions of expected value and variance, and hypergeometric is sometimes viewed as a more precise version of hypergeometric. The only difference is p and 1 minus p have new forms because we know that p is k over n and 1 minus p is its complement. So for hypergeometric, what we're going to have is the following. So hypergeometric versions are going to be as follows. So the expected value of hypergeometric will be equal to n times k over capital M, and the variance will be equal to n times k over capital M times its complement, and also a new piece of information, capital M minus little n over capital M minus 1. And what this does is it adjusts for our finite population. And this little number, capital M minus little n over capital M minus 1, will come back a little bit later once we start talking about hypothesis testing. Right? So these are the formulas for the expected value and the variance of a hypergeometric random variable. Now let's get into a real-life example on how this can be used. Suppose you have a room of 27 individuals, 5 of which are sick, the others are not sick. And let's assume that you select a group of 7 at random from this room of 27 individuals. So what exactly do we have here? So we have that the population size is given to be 27, so let's let n be equal to 27, and we're selecting a group of 7 individuals. That's going to be our population size, little m. Also, let's define success to be equal to sick person, which means failure in this context would be not sick. Then from our definitions and notations, what we have here is that the number of successes in our population is going to be 5, and the number of not sick people will be equal to 22 minus 5, which will be equal to, what would that be? 17. There's 27 people in our population. So 27 minus 5, that's going to be 22 not sick people in this room. So if we select a random sample of 7 people and we assume that the sickness of one does not affect each other, let's assume, then what we're going to have that x is hypergeometric. So the first thing that we need to figure out is, does x have a range? For example, does it have a minimum value that it could be? Does it have a maximum value that it could be? Actually, it has both. So the minimum value that x could be is actually equal to the maximum of the two numbers, 0, and n plus capital K minus capital M. So for our particular example, that's going to be equal to the maximum of 0 and 7 plus 5 minus 27, which is the maximum of the two numbers, 0 and 12 minus 27, which in this case is equal to 0. So for our particular example, the minimum value that x can be is 0, meaning that it's possible that 0 people in our sample could be sick. And you might be thinking, well, is it really possible that x is greater than 0? So let's look at our particular scenario. Let's actually draw a few values. So let's assume that we have SSS, SSS, failure, and failure. And let's assume that we grab this particular object. So n is equal to 5 in this case. The number of successes, k is 1, 2, 3, 4, 5, and 6. And capital M minus k is going to be equal to 2. Right? So notice that if I grab 5 people, then it's possible that these 2 are located here. But regardless of which sample of 5 that I do, for example, I could have done that group of 5, I could have done that group of 5. There's actually several groups of 5 that I could target here. All right, so 1, 2, 3, 4, and 5. Notice that it's not possible for me to have 0 successes within our sample because we do not have enough Fs to sort of, destroy all of our sample. right? So we can say that if n is bigger than 2, at least one success exists there in our sample. And if n is greater than 3, our sample is greater than 3, and 5 obviously is, then at least 2 successes are in our sample, and so on. So that's pretty much why the minimum value of x is not necessarily equal to 0. Right, so we have that the minimum value of s, through mathematical combinatorics is the minimum of 0 and m plus k minus capital M. Similarly, the maximum is also not necessarily equal to the population size, but it's the maximum. So this is the minimum of x, and the maximum of n and k, this is actually equal to the maximum value of x, right? So that's actually pretty interesting. Again, that should be the max, right? So the min is equal to the max of some numbers. The max is equal to the min of some numbers, right? So let's just clarify that. Right? So this is going to be the minimum and maximum values for a hypergeometric random variable. So therefore, we can state, generally speaking, that x belongs to the interval, so the minimum or the maximum of 0, m plus k minus n, all the way up to the minimum of n in capital K. And I'll let you sort of think about why the maximum is not bounded above by little n or capital K. So for us, the maximum came out to 0, and the minimum for this you should verify to be equal to 5. So for us, x ranges from, for our example, 0, 1, 2, 3, 4, and finally 5. So we could have anywhere from 0 to 5 sick people within our sample. So for our example, what is the expected number of sick people in our sample of size 5? Well, from the formulaic perspective, that's going to be n times capital K divided by capital M, which is our sample size of size 7, the number of sick people in our population 5, and our population of size 27. So we do expect there to be about anywhere from 1 to 2 sick people in our sample. Now, again, we could have 0 people in our sample that are sick. We could have all of our sample to be equal to sick. But keep in mind, our sample is of size 7. So we always will have at least 2 healthy people within our sample, because the maximum number of sick people is 5, which is going to be the number of sick people that are within our population. Right? Also, you can find the probability that we have exactly 4 people that are sick, because 4 belongs to 0, 1, 2, 3, 4, and 5. Using our PMF formula, that's going to be equal to, so there's 5 sick people total. We want 4 of them, regardless of the order. There are 22 not sick people, and within our sample of size 7, and 4 of them are sick, that means 3 of them are going to be healthy. And then out of our population of size 27, we're going to be grabbing a sample of size 7 from it. Any rearrangement will do, and that's going to come out to approximately 0.0087%. So it's not that likely. So let's also do the probability that x is at least 4, or more than or equal to 4. And keep in mind the largest value that x can be for this particular example is going to be 5. So that means this is going to be the probability that x is equal to 4 plus the probability that x is equal to 5. If we write this in combinatorics form, what will that be? So the probability that x is equal to 4 is, again, 5 choose 4 times 22 choose 3, all over 27 choose 7. Note that 5 plus 22 is 27, and note that 4 plus 3 is equal to 7. That will always be the case for this structure. And then let's look at 5. So we have 5 choose 5, so we have all the sick people in our population inside of our sample, but we still have 2 people left that are not sick that are always going to be there, and then we have our 27 choose 7 rearrangements of our sample from a population, and you should find that that's approximately equal to 0.0089%. right? So that's how you can actually work with the hypergeometric distribution to find probabilities and expectations of samples where you have ratios of successes and failures rather than the percentages of successes and failures like we had with the binomial perspective. Now that we have the generalization of binomial into hypergeometric, which translate percentages into ratios, now let us see if we can do the same for the multinomial into what we call the multigeometric probability mass function. So again, the multinomial worked in this particular form with the very important observation that these were percentages, not ratios. And a couple things that need to be true for this to hold and work is that n1 plus n2 down to ng is equal to n, and p1 plus p2 down to pg was equal to 1. And in case you do not know what g is, pretty much what we have here is we're partitioning our probability space omega into a bunch of pieces, a1, a2, a3, and ag, where g is equal to 4 in this particular picture. So what we're going to do now is, instead of giving percentages, now we're going to have ratios for all g of these regions. So as usual, we're going to take our probability space omega, and we're going to be partition it into, let's say, 3 categories. And here is going to be our event space E, and our goal is to find the probability of E. We have 3 regions, so let's call them A, B, and C. And let's also suppose that we know the size of our probability space omega, that's going to be equal to m. Let's assume that the size of the event space is equal to little m, and obviously we should know that n is less than or equal to capital M. Let's also assume that the size of A is known, let's call that Ka. The size of B is known, let's call that KB, and the size of C is known, let's assume that's KC. So if I were to select one person at random from this population, then what is the probability that it's equal to A? Well, that's obviously going to be Ka divided by capital M. Pb will be equal to Kb divided by M. And the probability that it's C will be equal to Kc divided by M. That's assumed that you select one person from this population. But if we want our particular event to be some particular structure of our sample, and particularly we want XA A's, and let's assume that we also want XB B's, and let's also assume that we want XC C's in our population, right? So we want that and that and that, in particular where XA plus XB plus xc is equal to our sample size, then it should follow pretty much a similar structure as that of a hypergeometric random variable. So for our particular structure, where we have xa's, xbb's, and xcc's, which I will just abbreviate as x hat, this will just be equal to our combination. So we have ka's, and we want xa of them. And then we have kbb's, and we want xb of them. And we want kcc's, and we want c of them, all divided by our rearrangements of our sample, n choose m, and we have this particular structure. But could we partition our probability space into more than 3 categories? Of course you could. So generally, let's assume omega is partitioned into G categories or G subgroups. Then the probability that our sample has that particular structure, x hat, will be equal to k1x1 times k2x2 all the way down to kgxg all the way over n choose m. So this is sometimes referred to as the multigeometric probability mass function. You will also see some people call it the multivariate hypergeometric. That's another name for this, right? But I'll just call it a multigeometric PMF since it pretty much stays in parallel to the other ones. So some formulas that you probably can guess. So the expected number of objects of type J, where J ranges from 1 to G, will be equal to n times kj divided by our population size m, and the variance of xj will be equal to m times kj all over capital M, 1 minus kj over capital N, so that's np1 minus p in disguise, and then capital N minus little n over capital M minus 1, our little finite population correction factor. So those are the theoretical aspects associated to a multigeometric distribution. Now let's do a real-world example of this to sort of see how it works in practice. So suppose that there are 23 animals at a local animal shelter consisting of 5 dogs, 3 turtles, and the rest cats. So let's look at our particular population structure. So capital N will be equal to 23, and this is partitioned into 3 categories: dogs, turtles, and cats. So the number of dogs, which I will represent by K1, will be equal to 5. K2, which will represent the number of turtles, that's going to be equal to 3. And then K3, this is going to correspond to cats, is going to be 23 minus 5 minus 3, which you should be able to find to be equal to 15. Let's also label these so that we do not forget, since we are naming them K1, K2, K3. You could also call it K-dog, K-turtle, and K-cat if you want to subscript with words. But this is dogs, turtles, and cats, right? And also keep in mind, this allows us to build ratios for probabilities, not percentages, right? Not necessarily percentages anyway, right? Because ratios can be converted to percentages, but percentages cannot be converted backwards into meaningful ratios, typically speaking. So now what I want to do is I want to select a simple random sample of 7 animals from this shelter, and let's assume that I'm interested in getting a particular structure, x1 to be equal to 2, x2 to be equal to 1, and x3 to be equal to what? So 2 plus 1 is 3. I have a total of 7. That means I'm allowed to have 4 of the last character. So keep in mind, x1 corresponds to the number of dogs, 1 corresponds to the number of turtles, and 4 corresponds to the number of cats in my particular sample. So what is this going to be? So this is going to be equal to all of the rearrangements of these 7 animals. So that's going to be equal to 7 factorial over 2 factorial, 1 factorial, 4 factorial. But keep in mind, I cannot just use the multinomial distribution and just replace our p's with the ratios, because it doesn't account for the rearrangements of the samples. So since we have ratios, not percentages, this is going to be a multigeometric structure. So what are all the rearrangements of our dogs? So there's 5, we want 2. What about our turtles? So there's a total of 3, we want 1. And for our cats, there's a total of 15, we want 4. And then our population size is 23, and we are choosing 7 of them. So once we actually work out this math, this is going to be approximately 0.1670. So there's a 17% chance that when you select a random sample of 7 people, then you're going to have this particular structure. And if you do that particular structure, then the expected number of cats is going to be equal to n times 15 divided by 23, which is approximately equal to 4.57. So you expect anywhere from 4 to 5 cats within your sample. So that is a probability mass function perspective of hypergeometric and multigeometric random variables. And in the next video, we'll also do a generalization of the binomial distribution as well. So I hope you enjoyed this video, and I'll see you in the next one. Take care.